And as we move forward to this next section about data visualization, it might bear worth noticing that in academia, you usually are able to define the problem that you're dealing with. So you can cleanly bound it, and you can say that, well, what's outside of these bounds is not my problem. But in other contexts, you're not able to really do this often. But you may have some unexpected consequences, and you may need to uh, bear those. So just to keep in mind as we progress in this course, these settings where you're doing hypothesis testing, they are already highly structured, highly controlled settings, in the sense that you have spent a lot of time to find this situation where you can, as Fisher stated, where you seldom get a large p-value. So you quite rarely fail to get statistically significant findings. And so this context of context of justification, we contrasted with the context of exploration. It comes quite late in the knowledge gathering cycle, so to say. But it may never come in many effects. So some things are just too moving too fast, what we call also non-stationary. So once you get a hold of what's happening, you find the pattern, and the pattern already changes. So just keep that in mind. So let's talk about data and presenting data and what we can do with. So just to begin this section to get everyone on board. So what's usually done in statistics is that we have a population, and we don't want to make measurements of every single person in the population. So what we do is we draw a sample from the population, and usually if it's not a random sample, there are huge pains that come with it, but everything works much more smoothly when you get a random sample from the population. And we want to look at this sample and make inferences about the population. So we want to look at, take a part of the world, look at it, and want to infer, try to infer what the rest of the world looks like. And you can, for example, think of people getting surveyed for what are you going to vote for in an upcoming election. The whole point of that is to try and how many people will vote for them. And as we know, those surveys are not very famous for their accuracy. But anyway, so who ends up in the sample that we take? It depends. So one person, if we do some product testing, for example, there might be one person that was about to enter our study, but they fell sick, or another person who just happened to bump into the invitation and took a part in our study, and so forth. So it depends on who gets to participate in the study. And we don't want results that are completely dependent on who happened to walk across the invitation to participate in the study. which means that there is uncertainty in whatever we measure based on like the people who went. So if you only survey two people, if those two people would have been different two people, you might have gotten very different results. But if you sample 10,000 people randomly from the population, it doesn't really depend that much anymore from who exactly the individuals are. So if you remember, we spoke about the evidence of absence and not being the same as absence of evidence. And we're going to look at our first data visualization from this one. So this is an approach that's called equivalence testing, but I'll walk you through the process and what all of this means. So we have here in the black box that signifies an observed effect. So it could be a difference, for example, a difference between two means. So let's say that we are running a fundraising campaign, for example, for a charity, and we have two advertisements, and we want to look at, okay, so which one on average brings in more donations. And we observe that, okay, so on average, advertisement A brought in what is this, 70 euros or dollars, and $70 more than advertisement B. So that's where the box is. And so what's and the wings that across the box are our confidence interval. We don't need to go into the detail, but we could as well call this variable interval, which basically means well, it basically means the uncertainty around our estimate. So we happen to get 70, but it could have as well been something like minus 200 over here. And in this dashed line, you can see a point where the effect is exactly 0. And on left and right, we have a threshold of practical significance. So this is the smallest effect size of interest. So let's say it's $480 or 480 euros. And because we have to pay for the advertisement, pay for the media who delivers the advertisement and so forth. So we are not interested in getting just a very small differential between the two things. Or in the case if you're trying to enable more physical activity in a school class, you're not necessarily interested in physical activity interventions or ways to do that which are only very, 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 very small. And for very, very, very small effects, you also need a very large sample, because anything that's very small needs a very good telescope to observe. And we can think of our sample size as the resolution in our telescope. So this line and the box, what they depict here is that if we would get a result like this, we would say that because it crosses, the wings cross the 0 line, so we would say that, well, it could be that this is 0, but it really looks like it's not practically meaningful, because it doesn't cross the line that indicates the smallest effect size of interest. Another option is that the line doesn't cross the zero line. So this means that we would conclude that, okay, so this effect, so this difference doesn't look like it's zero. So looks like there's a difference between these two advertisements, but it also looks like it's too small to actually matter. So we don't really care about the small effects. And we could have a situation like this where the effect, it looks like it's not zero, and it also looks like it might be big enough to actually matter to cover our costs and so forth. And then in the optimal case, we find something like this, where it's not zero, and it also doesn't cross the area which detects the we don't care effect size distant area. You get the point. So if you want to have a look, so there is I wrote an article about this, which doesn't show here. There's, well, this thing is called equivalence testing. If you're interested, but it's not that important. This the main the broad strokes here are the most relevant. But in the worst case, you might end up with something like this. And in this case, it is probably the most honest thing to say is to just realize that this study might have not. It might have been best to not do this study because there's just too much variance to actually say anything about anything. And it might be that later there will be a meta-analysis which will collect a lot of these small effects which are from the same context that you've been working on, and they will find that, oh, well, actually there is this sort of much smaller effect, or that the effect is actually zero, or wherever the effect goes. But it also might be that there is a meta-analysis that collects all these small effects and tries to doesn't realize that these are very heterogeneous or unique contexts that shouldn't be combined, and try to come up with try to answer the question, what is the real mean difference, whereas there is no there may not be any true underlying mean difference here, because the effect is non-stationary in time and across time.